Hello and welcome back to Dr. Logic Awkwardly Does Logic in her office. In the last couple of videos, I've introduced to you the truth tables for each of the various propositional logic connectives: negation, conjunction, disjunction, and the conditional. In this video, I'm going to just work you through how you can take those tables and combine them together to determine the truth values of even more complex formulas. So I've got a couple things up on my whiteboard already, including just so that you can refresh your memory, the truth tables for each of the connectives. And then I'm going to illustrate how to put them all together by asking, what are the possible truth values of this formula here? So if P then Q, then either R or Q or not P. So there are three atoms. The first thing that you want to do is make a list of all of the atoms that you have. So we have P, Q, and R. And then we need to figure out what are the possible truth value assignments for each of these letters. So it could be that, sorry, let's make that T. They could all be true, or some could be true and some could be false, or they could all be false. Now, when you have a certain number of atoms like this, you can always determine how many values you have to have in your table by looking at the number of atoms and taking 2 to that power. So if you have 3 atoms, if you have 1 atom, you need 2 lines. If you have 2 atoms, you need 4 lines. If you have 3, you need 8. And we'll rarely use formulas that have more than 3 because 16-line truth tables get very long to write out. But then once you know that you have 8 lines in your table, with your first atom, you make half of them true and half of them false. Then of the ones that are true for the next atom, you make half of those true and half of them false. And then of the ones that are false, you make half of them true and half false. And then the last row is always going, the last column is always going to be alternating T's and F's all the way down. And then if you fill your table out this way, this will guarantee that you get every single possible combination of truth value assignments for the atoms. So we've got a very complex formula here, but if you look at it, you can see that within it, there are less and less complex subformulas. So some of the subformulas that we have in this formula are if P then Q, we have not R, we have not P, we have not R or Q, and then we have this disjunction here. So these are all of the subformulas that we have before we put things together underneath our main connective, which is this implication. So let's look at the smallest bits first. So Q here is a subformula, but we already know the possible truth values of Q because we can just look at the column that we've written down. So the next ones that we want to look at are going to be the formulas not R and not P. So whatever we have in the column for P, it's going to be the opposite in the column for not P because of the table for negation. So not P is going to be false, 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 true, 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 true. My lines are not matching up very nicely, are they? Let's see if we can draw some in. So that's one line of our table. That's one. Oops. That's one. And here's where they kind of get a little bit weird. And this is why truth tables are best drawn in notebooks and not on whiteboards. Even if this wasn't an electronic whiteboard, I still wouldn't be able to draw my lines straight. Anyway, same with R. So not R will always have the opposite truth value to R. So here R is true. This means not R is false. Here R is false, so not R is true. And we just go down alternating truth values all the way down. So that gets us kind of the next most basic subformulas. Then we take 2 of them, we take not R or Q and combine them together. Now, in the disjunction table, you can see that if you look at the values of the inputs, if either one of them is true, then the value of the disjunction is true, and it's only in the case where they are both false that we have something false. What we have for our inputs for this column is going to be the column for Q, and then the column for not R. So we look at the values here. So in the first row, we have true and false. So at least one of them is true, so the disjunction is true. Again, true and true. That's true overall. In the third line, we have false under Q and also under not R. So this is going to be false. Now I'll go through the other lines a little bit quicker. We've got true in our not R, we've got true in Q. So as long as I find at least one true, then we are good. And it turns out that all of the rows are true except for line 7 and 3, where they turn out to be false. Now, our formula here is getting a little bit kind of messy and hard to see, but the next combination that we have is the disjunction between this disjunction, so this complex formula, and not P. So here we're going to say, well, either not R or Q or P. Again, we want to look at the rows, and if either of the relevant columns in the row have a T, then the entire disjunction is going to be true. Oops, sorry, this is not, that should be not P. So now we are looking at this column and this column. So the simpler columns, we can now ignore them because we've already used them to construct the truth values of the complex column. So here we have false and true. That means this is true. False and true is true. False and false is false. False and true is true. True and true is true. True and true is true. True and false is true, and true and true is true. So this complex formula is only false in one case, in this case right here. Now, before we can kind of combine this with what's on the other side of the main connective, we need to deal with this complex subformula here. So we need to find out the truth value of if P then Q, and that will just use the atomic columns with the truth value assignment we started off with, because it's an implication between two atoms. So remember that an implication is false only in the case where the antecedent is true and the consequent is false. So these bottom four here, where the antecedent is false, we already know without even looking at the consequent that these four are all true. Now here, where the consequent is true, so Q is true, we don't even need to look at the antecedent to know that these are true as well. So the only cases that we have left are these two rows, and these are the rows where it turns out to be false because the antecedent is true, but the consequent is false. So there we go, false, false. Now we are at a position where we can ask ourselves, what is the truth value of the entire complex sentence? So if P implies Q, then either not R or Q or not P. So here's our antecedent column. Here's our consequent column. So now we need to kind of like looking backwards, looking the other way around. We can do the same trick that we saw with the P implies Q column. Look at the column for the antecedent. That's this one here, the disjunction. Everywhere where there is a T, we can put a T here because when the consequent is true, the entire formula is true. So it's true in all but one case. This last case, we need to double check, is not one of the falsifying cases. So it's not a case where the antecedent, P implies Q, is true and the consequent, not R or Q or not P, is false. In fact, in this case, both of them are false, so this turns out to be true. Now, this is particularly interesting because look at the column that is underneath our final formula. What you will see is that every single one of these is true. So it doesn't matter what assignment of the atoms we start off with, we're going to end up with a true formula. This is not always the case. Most of the time, if you write down a random string of symbols that's a well-formed formula and you do this kind of calculation, you'll end up with something that is sometimes true, sometimes false. Maybe you might get something that's always false. That's kind of unusual. Or you might get something like this, where it's always true. This is a particular type of formula that we're going to talk more about in the next video, but it's called a tautology. So there's no point at which it could ever be false, no matter what the actual values of the atoms are. Because of the structure of the formula, whatever combination of truth values you put in for the basic parts, the big part is always going to come out with true. So this is just one example of how to combine the truth tables in this more complex way. In future videos, because we're going to be doing a lot of these truth tables, I will give you methods for kind of shortening or making more compact the full representation of the table. Instead of drawing a column for each one of the subformulas, I could have just written the truth values underneath a column formed from the main connectives or the atoms in the large formula. Again, I'll show you an example so you see what I mean. But more importantly, we don't want to have to write out all 16 or all 32 or all even more tables of a truth table, because this gets tedious, and more importantly, it increases the chances that you'll make an error just by like misreading a true or a false, or writing the wrong thing down, or writing it down on the wrong row. So I will give you a method that we can use, particularly if we are interested in determining whether a formula is a tautology or not, that doesn't require us to write down the full truth table. So that's the shortened truth table method, and I'll introduce this to you in probably 1 or 2 videos time. In the meantime, go ahead and pick some random formulas, write them down, calculate their truth tables, get a sense of how all of the connectives interact with each other, and how to go from the truth values of the small parts to the truth values of the big parts. We're going to be doing a lot with these, so the sooner you get comfortable with them, the better. Hope to see you again soon. Cheers.